The dark matter story you were sold. The story starts simple. In the 1970s, Vera Rubin measures how stars orbit in spiral galaxies and finds a problem. The outer stars don't slow down the way Newton says they should. The rotation curves go flat. Then lensing studies arrive. Light from background galaxies bends more than visible matter can explain. Zoom out farther, and simulations show large-scale structure forming too fast unless extra gravity helps pull it together. The fix looks tidy. There must be more mass than we can see. Call it dark matter. Add it to the ledger and the math behaves. That's the version you learned. It's clean because it keeps gravity's rules intact and just pads the inventory. You get a halo around galaxies, a scaffolding for clusters, and a comfortable slogan, the invisible glue. Meanwhile, cosmology fits the pieces. The cosmic microwave background's acoustic peaks line up with a universe where non-baryonic matter dominates mass. Baryon acoustic oscillations trace a preferred scale frozen into the galaxy distribution that also points at invisible mass underwriting growth. Structure simulations fed with a dark component spit out filaments and voids that look eerily like the maps we draw. So why is anyone restless? Because for decades we've built traps and come up empty. Underground detectors waiting for a weakly interacting particle have reported hints and retractions, but no confirmed catch. Colliders searching for supersymmetric partners haven't produced the clear signatures once expected. Axion haloscopes keep tightening bounds. Lensing surveys improve statistics and still tell the same high-level story, but the warehouse shelves remain bare when you walk the aisles with particle eyes. The gravity ledger reconciles. The parts list refuses a serial number. Here, S where the metaphor from before earns its keep. Stop treating the missing as boxes no one can find in a dimly lit stockroom. Start treating it as unasked for detail. Mass equivalent correlations encoded in ways your current channels don't fetch as visible photons. Gravity integrates what's encoded, not what sparkles. Lensing is a readout protocol. Rotation curves are interface behavior. You're observing how the system answers under constraints, not its backstage props. Think about a table in a room you visit daily. It persists because the environment keeps retelling the same story about it. Many photons, many angles, many hands. Objectivity by redundancy. Now imagine a field you can't directly couple to with light, but that still affects motion through the gravitational ledger. The story persists for orbits and lenses even if your photometric channel is blind. That's not a conspiracy. It's an API boundary. You don't get quark-level pixels to fly a plane. You get lift as an effective variable. There's a micro-story that makes this land. A student maps a galaxy's rotation curve by measuring hydrogen emission lines far out into the disk. The curve refuses to dip. She runs a mass model using the stars you can see and the gas you can count. Still short. She adds a halo with a simple profile, one rule, a handful of parameters. The fit snaps into place. The curve isn't a confession that boxes exist in the dark. It's a signature that the interface enforces a stable answer under budget. Maintain flat rotation through an extended mass equivalent profile. Meanwhile, simulations lean on the same move. You can't resolve every star or supernova down to first principles, so you build subgrid models, effective prescriptions that capture how unresolved physics feeds back into resolved scales. You don't simulate every photon to get galactic winds. You write a rule that's been validated where you can test it. Dark matter plays that role in the cosmic story. It's the effective variable that stabilizes structure formation, while staying invisible to channels that would ruin the budget if everything had to glow. Critics fire back with modified gravity proposals. Change Newton or tweak Einstein on galactic scales, and you can fit rotation curves without halos. Fair. But then lensing steps in, clusters speak, and the cosmic microwave backgrounds peaks weigh the universe from a different angle. The same rule must pass every audit. Most modified schemes stumble across those independent ledgers or end up reintroducing a dark sector in new clothes. The point isn't to crown winners. It's to keep the efficiency pressure in view. The cosmos uses the cheapest variables that reconcile multiple constraints at once. So reframe the question. Instead of what particle did we miss, ask, what encodings does gravity read that our detectors do? If the answer is a particle, great. You'll find its handshake in some faint channel eventually. If it isn't, the dark component remains the interface's shorthand, an unrendered correlation field that still balances the books. Either way, the message is humbling. The universe doesn't owe you detail everywhere. It owes you consistency within your access. Here's the cliff we're walking toward. If boundaries serve as ledgers and budgets keep biting, there has to be a place where the storage runs tight. Not a crash, an optimization. In the maps, it looks like emptiness. In the equations, it looks like compression. And in the sky, it looks like a web with sharp edges and hushed interiors. That's where we turn next, where the universe keeps the books and what it renders when the quota gets real. Boundaries as ledgers, where the universe stores the world. To see where the universe keeps its records, start at the edge. Not a cliff, an accounting surface. Black holes taught the first lesson. Their entropy scales with area, not volume, as if the number of internal possibilities is written on the horizon like a ledger. In toy dualities we can solve, add SCFT. The whole bulk is reconstructible from boundary data with the logic of a quantum error-correcting code. Our cosmos isn't that exact lab model, but the message carries. Surfaces set quotas, and access decides what can be rebuilt. So think of horizons as interfaces with thermodynamic signatures. A de Sitter, like patch, has a temperature and an entropy proportional to its horizon area. Translation: finite state counts per observer, a faint thermal bath, and a hard limit on the distinct detail you can ever stabilize inside your wedge. You're not denied reality beyond. Your channels just can't fetch it. The ledger writes what many roots can certify and leaves the rest compressed at the edge. Objectivity fits into this like a glove. Quantum Darwinism says macroscopic facts become facts when many fragments of the environment carry the same information about them. A rock under sunlight writes its position into floods of photons, onto dust grains, into warmth in nearby air. Many copies, one story. Those copies live on boundaries, screens, sensors, retinas, memory surfaces, each a little edge where information lands and persists. The world doesn't keep a central database. It spreads the bill across interfaces that never stop broadcasting. Here's where it bends your intuition. You want the real to live in the middle. The math keeps pointing to the perimeter. Area laws for entanglement show up in ground states of many body systems. Cut space into two regions and the shared information scales with the cut, not the bulk. That's a storage rule. It says the cost of separating worlds is paid at seams. If seams carry the cost, seams carry the code. Now fold in horizons you can name. Particle horizon, farthest light that reached us so far. Event horizon, what could ever reach us if we wait forever in an accelerating expansion. Apparent horizon, the local threshold where outward light rays hover. Each is an access menu tuned to an observer's motion and history. Shift your path, your apparent horizon shifts. Two observers, two dashboards, same backend. No contradiction because causal contact prevents cross-checks outside their overlap. The ledger is personal by geometry, public by redundancy. A micro-story from the sky. A team points radio dishes at the afterglow of the young universe. They measure tiny temperature ripples and map acoustic peaks, then invert the pattern to recover densities, angles, and a tilt. They never saw the early plasma. They read its boundary signature like accountants reading a statement, totals, balances, constraints. The bulk, how gas rang, how gravity tugged, was rebuilt to the precision those peaks allow. The ledger lived on the sky's surface. Bring it closer. You speak a sentence in a busy room. The words hit walls, microphones, and minds. Minutes later, the content exists in notes, clips, and recall. You can't erase every copy without effort and heat. That's Landauer's price returning as policy. Interfaces, paper, glass, synapse became your horizons. They stored a compressed summary anyone with access can reconstruct. The room carried your bulk story on its edges. This is why voids read like quiet ledgers. You don't waste bits detailing uniform, low-gradient interiors. You spend them where boundaries sharpen, where signals reflect, where lensing turns geometry into data. Cosmology's web looks like a smart accountant's sheet. Thick lines where flows are strong, white space inside where nothing changes much. When you do see structure inside a void, it clings to a plane or filament, another seam where the code prefers to sit. There's a discipline hidden in all this. Don't confuse storage with simulation. Boundaries don't invent. They gate and certify. The holographic whisper isn't a claim that the universe is a flat movie. It's a reminder that finite access and area laws force compression, and compression makes edges valuable. Ask a finer-grained question than your channels support, and you won't get pixels. You'll get priors and symmetry-consistent answers the ledger can stand behind. Landauer's cost and horizon quotas set the rules. Efficient encodings are the result. One last step before we test limits. If surfaces carry quotas and horizons meter access, then the world you stabilize is the one you copy onto the edges you can reach. Photons, paper, silicon, other people. Your causal patch isn't a prison. It's a writable interface. That's why gravity reads mass-equivalent encodings even when nothing glows. That's why cosmic checksums reconstruct histories we never saw. And that's why, when storage feels tight, the universe moves detail from bulk to boundaries and keeps function while shedding grain. The ledger isn't hiding. It's the bright line where information lives. Cliffhanger, ready to see how the cap enforces silence and what that silence proves. The memory cap, reading the limits from smoothness and silence. Start with what didn't happen. If spacetime were a sloppy lattice, high-energy photons should arrive out of order after billions of light years, short wavelengths lagging or sprinting. Observatories watch gamma-ray bursts at ridiculous distances and clock their arrivals within brutal bounds. No dispersion worth bragging about. If holographic jitter haunted our baselines, paired interferometers should have caught a correlated shimmer. They posted tighter limits again and again. That silence isn't empty. It's the codec telling you it respects symmetries to a painful precision and won't pay for grain you can't verify. Cliffhanger. If the cap refuses flicker, where does the deleted detail go? Meanwhile, the sky behaves like a patient compressor. The cosmic microwave background is not a mural of surprises. It's a disciplined spectrum of acoustic peaks that a handful of numbers decode. Add amplitude, tilt, matter fractions, and the whole drum chart unrolls. On larger scales, the web is sharp where gradients live and quiet inside. Filaments sparkle with lensing and flows, voids mostly yawn. The pattern keeps pointing the same way. Spend bits where many channels can test, compress where no channel can. Why would the world be this thrifty? Because your patch has a quota. Horizon thermodynamics sticks a number on it. A de Sitter, like horizon, carries an entropy proportional to area and a faint temperature. Finite area means finite state count for what you can stabilize. Within that budget, the codec prioritizes long wavelength, Lorentz respecting fields, and high redundancy macroscopic variables. Ask finer grain questions than your channels support, and you get priors and symmetries, not pixels. There's an efficiency inference hiding in the smoothness. Compression isn't random loss, it's a rule book. In information theory, the best codes pack common patterns into short descriptions and shove rare, untestable detail into longer, seldom used strings. Physics feels similar. Invariants, conserved currents, geometry that many detectors agree on get promoted. Short range, low redundancy twitch gets averaged out. The codec isn't guessing, it's optimizing for predictive power under a storage cap. Now imagine what happens when requests push the edge. More instruments, deeper exposures, tighter timing, more potential writes against the ledger. Systems under pressure don't crash first, they compress. They lean on redundancy, they thin the grain. You can see the tell. Coherence at large scale stays rock steady while small scale freedom is rationed. Not broken laws, budget enforcement. The cap doesn't show up as an error message. It shows up as unwavering smoothness where you expected flicker, and as suspiciously tidy summaries where you expected clutter. A micro story from a control room. A collaboration stacks years of gamma-ray burst light curves, binning photon arrivals by energy and distance. The algorithm hunts for a trend, a whisper of energy-dependent delay building with path length. The final plot sits flat within uncertainties. Someone exhales through their teeth. No headline. Then the pie taps the figure. This is the headline. The bound is a design spec. Meaning, whatever the substrate is, it cancels lattice like artifacts so well that even our most ambitious baselines can't pry them loose. Cosmological horizons add another layer. The particle horizon drags new light into reach as time passes. The event horizon shaves futures away in an accelerating expansion. Both carve your request space. You don't render what no signal can fetch, and you don't keep explicit what a handful of parameters and stable dynamics can reconstruct later. The codec delegates, cache constraints at the edge, let bulk behavior decompress only to the precision observers can test. That's why the acoustic peaks read like checksums, why large-scale correlations stay crisp, why interiors go smooth. Information tides follow. As more questions push the boundary, more copies, wider redundancy. The variables that many channels can cross-check win bandwidth. Others get pushed into effective descriptions. Detail isn't deleted. Landauer won't let you do that cheaply. It's offloaded and recoded into boundary constraints and coarse-grained rules. You keep function, lose grain. A halo profile stabilizes rotation without tracking every clump. A lensing map stabilizes mass equivalence without tagging every photon source. Same ledger, smaller bill. So what's the human readout? Stable large-scale coherence with strict local quotas. The universe keeps your big modes predictable and your micro-ambitions honest. You'll measure null dispersion, hear the quiet of interferometers, and find that voids prefer emptiness by design. You'll also catch the system paying up where it must. Sharp edges, trusted invariants, ubiquitous summaries the ledger can defend across instruments and epochs. There's a discipline in listening to silence. Each null trims fantasies and tightens the codex spec. No dispersion. Respect Lorentz symmetry. No holographic jitter. Hide discreteness under entanglement structure and area laws. No crowded features in the early sky beyond the acoustic playbook. Trust that a handful of inputs and faithful dynamics can write a whole epoch. Every non-event is the cap, whispering what it will never pay for and what it will always underwrite. Which sets up the next move. When storage runs tight, systems don't shred, they reorganize. Compression wins, eviction targets low redundancy detail, and boundaries shoulder more of the bookkeeping. In the maps, that looks like smooth voids and sharp seams. In black hole physics, it looks like islands and page curves. In your life, it looks like summaries people can actually agree on. The cap isn't a crisis. It's the protocol guiding the handoff that comes next. Deletion events without deletion, offloading and recoding. When systems hit the cap, they don't hit the shredder. They pivot. Physics prefers to recode, not erase. Landauer's principle sets the price tag on oblivion, so the universe pays its bills another way,